Broomfield. Charles is cyber analyst in HSS EDI at Mitre Corporation. He is currently the task leader for critical infrastructure model building application, which is designed to partially automate the development of simulation model for critical infrastructure networks. Additionally, Mr. Broomfield has supported efforts related to the assurance and risk management of artificial intelligence and the effective use of data across Homeland Security enterprise. Mr. Broomfield received his BS in Computer Science and BA in Business Management from Knox College, Galesburg, Illinois. He is currently pursuing a ME in Cybersecurity Analytics from the George Washington University. So he will be talking on simulation model building for critical infrastructure. So, Charles?
Great, thank you very much. Happy to be here. I just gave a portion of this presentation a couple of days ago at an SF event. These slides, they're the only slides I have which are publicly released. They were originally designed for a shorter time slot, but that just means that y'all will get even more detail and a little more insight into what we're thinking about as we're trying to develop this. So let me get these into presentation mode for you all. Alrighty, and then let me just readjust some of my windows so I'm able to see everything. I'm going to see multiple setup, of course. All right, so yeah, what I want to talk about today is simulation model building for critical infrastructure, and really specifically the electric power sector, because that's where we've started with our efforts. So as you just heard, my name is Charles Broomfield. I've been leading a team from the Homeland Security Systems Engineering and Development Institute, which is operated by MITRE. It's an FFRDC operated by MITRE. And right now this work is in support of the DHS Science and Technology Directorate Data Analytics and Technology Center, or S&T DATSI. We also work with several other researchers, 3 different professors who work as subject matter experts for us as well. It gives a lot of really good insight and expertise on these topics. And we really believe that simulation models of critical infrastructure networks could open up some really, really exciting applications, and we'd like to see more of those applications being deployed. But right now, the simulation models that are required that underpin all those different applications are very hard to build, they're very expensive to build. And I'm sure I'm speaking to an audience that understands a lot of these challenges given the title of this task force. Now, something I do want to point out here is that, you can notice my slides are titled simulation model building, not digital twin building. So the work I'm speaking to today does not produce a full digital twin, and that it's not going to be connected in sort of real-time feedback with the network that we have the model of. But our hope is that the high fidelity simulation model that does come out of our work can make the digital twin marketplace more accessible to more and more people. And can at least sort of be an underpinning of full digital twins, even if it's not a digital twin when it comes out of the process that we're working on. So we think we can have some real impact in this space by making it significantly easier to develop high fidelity simulation models and then enable downstream innovation in the critical infrastructure market and in the digital twin market. So let me advance my slides here. Of course, I'm going to jump to a different window for that. 1 second. There it is. Alrighty. So as I said before, I'm going to focus on the electric power sector for most of this talk. And what we've learned is that at least in the electric power sector, and I think this is probably true of many other critical infrastructure sectors as well, is that many owners and operators of these networks do not have high fidelity simulation models of their own networks, much less full digital twins. And for the purposes of this talk, when I'm referring to high fidelity simulation model, what I really mean is that a model can perform transient stability analysis. So in terms of timescales, about 1 second. So what a lot of owners and operators do have is steady state models. So what these models can do, given a perturbation to the network, they can determine what the new equilibrium point will be after that perturbation, after the restabilization of the electric power network. There will be some graphs later that will hopefully demonstrate this a little better. What a transient stability model can do is simulate how the grid restabilizes. So we can get insight from when the perturbation happens to that to the restabilization. We can see what goes on because it's not a smooth curve. It's sort of a bumpy ride back to stabilization, and we really want to have insight into that path. And the reason it's so important for more owners and operators to have these high fidelity simulation models is because we think these models can be really useful for solving some of the really pressing challenges that this sector faces in particular. So a few of them are included in this slide here. One of the really big drivers is renewable energy. This is really demanding rethinking of the traditional network architecture because power is coming from different places, it's coming at different speeds, and higher fidelity simulation models were really needed to manage these new networks effectively, efficiently. And we just really have to change how we think of networks, especially with solar coming up from the distribution level. Now it's really changing this paradigm of power going from generation through transmission to distribution. Now power can come up from distribution. So having high fidelity models that can keep track and understand these power flows is going to be really important for us. Another issue is that blackouts are so difficult to reconstruct, and they're also difficult to predict if all you have is a lower fidelity simulation model. So these blackouts are becoming even more common given severe weather, a lot of different threats and impacts to our electric infrastructure. And then at the same time, our networks are also becoming even more connected, which increases the complexity of those networks. It makes it more possible for a change in one part of the network to then impact somewhere else on the network. So again, it's useful to have high fidelity simulation models to really understand what will actually happen. If a line is to go down, if a generator is to go down, if a substation is to go down. It gives us a lot more insight there. But the real motivation behind a lot of this work is the threat to critical infrastructure from cyber criminals and nation states. And that's why this work is being pushed forward by Department of Homeland Security. What high fidelity simulation models can do is help us better predict, okay, what are the consequences of that attack? And also, very importantly, what would be the impact of different mitigations? What's the best way to defend and harden our networks against these attacks? But at the end of the day, what we really want to see is we want to see our critical infrastructure become more efficient. We want to see it become more reliable, and we want to see it become more resilient. So these three examples that I just talked about sort of map to these three different overall goals. The efficiency of normal operations, the reliability against small, common perturbations that might happen, like a power line going down, and then more resilient to really big impacts and our ability to maintain that critical infrastructure for all our citizens. So what we really want to see is we want to see high fidelity simulation models in the hands of all of the people who could use them, because these models can be used to support these purposes that we would like to see. So jump to the next slide here. For the remainder of the talk, I want to cover just four big topics. And first is why developing these models is so difficult, right? So much of our work is trying to get these models into the hands of different people. So why don't they have them? Why are they so challenging right now? Second, I'll talk about the two different ways that we really see automation being used to decrease development time without requiring a huge amount of information from the end user, because that's also a burden. Third, I'll give you a tour of the critical infrastructure model building application, or SIMBA, which is what we sort of refer to the process that we're building to try and help either solve this problem or at least alleviate that problem. And then lastly, I'll just talk about some of the design principles that are shaping our work today, as well as really shaping our work in the future as we continue to develop this and try and push this forward. So, as I said earlier, a lot of electric power owners and operators don't have the high fidelity simulation models of their own networks, much less digital twins. But these models are very useful. So the question is, well, why don't they have these models? What's getting in the way of them having this tool, which we know can be used for so many different uses? And the short answer is because building these models is really hard. So one of the big challenges that we've heard is just how time consuming it is, because it can take a very long time to assemble a simulation model of an entire grid that we're trying to model. So even just getting your head around all of the infrastructure that's out there takes a lot of time, much less truly understanding all of the different factors that are going to influence how those components behave in the real world. Now, this is sort of the second challenge, which is just the amount of effort that goes into gathering all of this data. Because traditionally, building a high fidelity simulation model requires a lot of experts and a lot of work to collect all the precise parameter data for all these different components, which we need to understand to really model this system well. Now, this is a really difficult process, and it also really does not scale very well. It becomes, exponentially more challenging as the network grows because there's so many connections and so many parameters to take into account. But you need these accurate estimates of all these model parameters if you want to have confidence in the simulation results that come out of that model. And I don't think that any of this is by much news to any of you. You probably have worked in the space for even longer than I have. But either way, this of course means a lot of experts spending a lot of time, a lot of effort to build a simulation model. That's going to mean that building a simulation model costs a lot of money. And that's worth it for some owners and operators. Some owners and operators definitely have high fidelity models of their systems, even full digital twins of their systems, but these are not within reach for everyone. And we would like to see this to be in reach for everyone. So about 85% of the electric power grid is maintained by private entities right now. And a lot of these entities, all of these entities are driven by economic incentives. So for some utilities, the cost of developing these models is just out of reach. But again, there's so many benefits to having these models, not just for that utility, but for the people who rely on those services. So what we want to see happen is we want to get these high fidelity simulation models into more people's hands. Because we'd like to see more people benefiting from the applications that are enabled by these models, and we'd like to again improve the efficiency, improve the reliability, and improve the resilience of our critical infrastructure for the American people. So if we want to get these high fidelity simulation models into more people's hands, these are really the problems that we have to solve. We have to reduce the time, we have to reduce the effort, and in doing so, we have to reduce the cost associated with developing these models. And that's where we hope we have some good news, because we really think that some of the steps of developing these simulation models can be partially automated. And there's really two parts of development in particular that we think can really be sped up potentially quite dramatically. So the first thing that we think could be partially automated is this initial assembly of a simulation model. Because these critical infrastructure networks, and especially electric power networks in particular, are extremely large and complex. So on the right, you're looking at a map of the US energy grid. And as you can see, it's sort of a mess. There's just a ton of stuff. And this is just transmission, not even mentioning distribution. But as complex as these networks are, they're built out of the same core components, right? So we have generators, we have substations, we have transmission lines. And there's really not that many different types of each of these core components. So imagine you had a library of all of the different transmission grid devices, and that library would store the parameters for these different particular components, right? That's not a massive database. It's large, but it's not massive. And if you did have this library, then what you could do is you have all of the building blocks you need already, right? So you would just need to know how to connect them all together, and then all of a sudden you would have a model of the entire network. So what this enables, instead of building a simulation model from scratch every single time you're trying to do this for a network, what this enables is you can effectively build it out of Legos. So at least in theory, this model assembly step would get easier with scale as this library becomes more and more complete. And the dream scenario is you have absolutely every single component that's on the network already stored in your library. All you have to do is look up the data that you need. So this doesn't exist right now in the electric power sector, but it's not impossible for something like this to exist. And something like this does exist in other domains, right? There are libraries of component models used to develop other things, for example, video games or simulations, other stuff. So we think this can exist. It just doesn't right now. But if we had this for the electric power sector, we could at least develop a rough outline of a simulation model of the entire grid, right? It wouldn't necessarily be perfect unless you had, absolutely perfect parameter data for every single component, which is a little unlikely. But it would maybe be 80% of the way there with much, much less work than this currently requires. So even though this doesn't automate the full process, this could be really, really valuable in speeding up the time to develop these simulation models. Now, the second step that can be automated really relies on breakthrough capabilities of machine learning, which of course is all the rage right now. But traditionally, machine learning has not been present in this process. Traditionally, simulation model has been built by measuring the parameters of the network, either on a real-world system itself or a physical replication of it, And then those parameters that you somewhat manually measure form the basis of a simulation model, which is then used to predict the operations of that network under various conditions, right? Then we get the simulations out of that model. So this workflow, which we're sort of seeing on this top line here, that requires a lot of time, a lot of cost, all the things that we just talked about earlier. So getting all these parameter estimates in a relatively manual process is just a huge engineering cost. But there's absolutely tons of data that already describes these electric power networks. And this domain really has some of the most incredibly precise sensors there are. So if we can leverage that, this is a really natural application for machine learning, because where there's a lot of data, there's usually good applications for machine learning. So what we can do is we can flip around the traditional problem. So now we're solving an inverse problem, which you're seeing on the bottom here. Because if we already have data describing real world network operations, right? We already have the frequency over time for all of these electric generators. Then what we can do is we can feed this data, this real world operational data, back through a machine learning process, and we can accurately estimate the real underlying parameters that produced that original operational data, right? And then we can take those parameter estimates, plug them into a simulation model just like before, and all of a sudden we have a refined, pretty accurate simulation model without having to go through this whole process of measuring all the parameters very precisely from the start. We let the machine learning do that. And the reason, by the way, that this works pretty well is that we're not estimating time-dependent parameters here, right? So this is a big concern whenever machine learning comes into the picture, because we don't want to. Generally, machine learning can only work on data that it's already seen. But in this case, all we're using machine learning for is to identify time-independent variables, right? We're trying to understand the physical parameters, like the inertial coefficient and the dampening coefficients, for example, understanding those coefficients of the electric power generators, which don't change over time. So if we understand these parameters, then we can have a ton of confidence in the simulations for many other events, even events that we've never seen before. So again, we're just using data from the observed network behavior using machine learning to understand the physical characteristics of the network. And it's those physical characteristics, once we understand them, then we can plug those into a simulation model. Now, by the way, you can also see the difference between, I was talking earlier about steady state versus dynamic simulation here. You can sort of see that in the graph here. So these graphs that you're looking at are dynamic simulation. You're seeing a perturbation happen at time step 1, and you're seeing it restabilize to time step, the perturbation ends time step 4, and then it slowly restabilizes. It's about restabilized around time step 15. With a steady state model, all you would really see is the state of the generators at time step 0, and then the state of the generators once things had restabilized after the whole event. You would miss all these wiggles and the impacts as the stabilization is happening. But this is really why, between these two processes that I just talked about, this is why we think it's possible to build high fidelity simulation models without a ton of data from the end user. Because the data can be simplified by either providing it by the reference library, which I just talked about, or they can be learned automatically in this step during this refinement. So let me take a couple of minutes to walk through what we're actually building. And we call this the Critical Infrastructure Model Building Application, or SIMBA. And we think of SIMBA as 3 stages, and I'll go into detail on these in a moment. But what I want to point out here on this slide is that these first 2 stages, right, the model generation stage and the model refinement stage, these correspond pretty much directly to the 2 steps I just talked about in terms of automation. So in the model generation stage, we try to automate the initial assembly of a simulation model. And here we're really speeding up the development by pulling in pre-stored data from a component reference library. So this model generation stage does produce a simulation model, but it would not be considered high fidelity, not at this point. So in the second stage, the model refinement stage, this is where we're using that machine learning process trained on operational data from a real electric power network to then refine those parameter estimates and end up with a refined simulation model, a high fidelity simulation model that can accurately perform transient stability analysis. And then that model can be applied for a whole bunch of different purposes in the last stage. So again, vulnerability analysis is sort of the focus behind our work, but there's lots of other things you can do with that. Now, I do want to emphasize that SIMBA is still in its early days, and there's definitely more research we'd like to do to get this deployed at scale for large power networks. But something I want to point out here, too, is that Well, we sort of show Simba as this huge overall, one big integrated process. The two functions that we're talking about here, these model generation, the model refinement, these are somewhat independent functions. So the model generation stage, the model refinement stage, they're all each at different levels of maturity. They each have very different challenges that need to be addressed to really make this work at scale. And what I think is maybe most important is that these can be independently useful. So I'll talk about that on each of these different stages. But even though we talk about combining all these things into Simba, I think there's some individual components that might be useful for different people's purposes without all the other parts of Simba. But so far, we've been trying to test Simba on mostly surrogate data, particularly when it comes to operational data. We're usually dealing with synthetic data. And we're mostly using well-defined test cases to test this out. But we're pretty optimistic we can eventually scale this to larger and larger networks and eventually have this be a really valuable tool for simulation model development. So let me jump into the individual stages, talk a little more in detail about them. So in the first stage, the model generation stage, this is where we're creating this initial rough simulation model, sort of an unrefined simulation model. And so the real value add of this stage is just creating a simulation model with as little information from an end user as possible. So at this stage, the only thing we want to require from an end user is this network map data, this sort of top block. And this network map data just consists of two things, which is one, the type of devices on the network, and two, just how they're all connected to each other. So this is basically just the topology of the network and an understanding of what devices at each node. Now, this is sort of the bare minimum amount of information we need from the end user, because if we don't have that data, then the simulation model just isn't going to represent the network of interest. So we have to have this data. And some of this data may even be publicly available. So we may even be able to reduce the load on an end user by pulling in other data. But at the end of the day, we definitely need whoever we're building a model for to come and verify that this is the correct map of their network. Otherwise, we're just not going to represent it very well. But the hope is that all of the other information that we need could be provided through a component reference library, which is this bottom block. And this is something we're trying to build out now. And this reference library would have models and parameters for different components, particular devices on that network. And if we don't have all the right information, then we can use informed default values instead. These can maybe get refined later, or maybe they won't be critical to the simulation. But especially early days, we probably won't have a complete, fully built out library. The assembler process on the right then is basically just the automated step. And what this does is it looks up what devices are on the network by looking at that network map data. It pulls everything, all the information that would be needed out of that reference library that describes all those different devices on the network. And then it connects everything together, again, informed by the network map topology. So the way I sort of think about this is the network map is just the instructions for how to build the network. The component reference library is like this big bin of Legos. The model assembler process just pulls all the Legos together, puts them together to form a simulation model by following the instructions. So right now, we're pretty much exclusively relying on open source data that we can find from manufacturers. And then that gets paired with the default values, which are already preloaded into open source simulation software packages for electric power networks. But in the future, we'd really like to see this library get built out during more early deployments of Simba, because we want to see this get more and more scalable and get more and more refined, more and more accurate as we develop this library. And this part of the process, from sort of a technical standpoint, is pretty scalable. So we've been using the high field data set from DHS as a surrogate. Basically, what the high field data set has is latitude and longitude of generators and transmission lines for the entire United States. So what we've done is we can take the electric power infrastructure for an entire state, and we can put it through the model assembler process. And what we get is a rough simulation model for the entire state. We can run simulations on it. Probably not very accurate using that surrogate data. It lacks a lot of information we would need, but we can test out this process. So we know that the challenge here for this stage is not really a technical challenge. We can definitely do this. We can definitely scale this. The real challenge for this stage, the real hurdle that has to be overcome to make this really, really useful for people like you and for others who might want to use this, is we just have to have the data for these components, right? We have to have a component reference library, which adds a lot of value. And no matter what I think we can add a lot of value just by scoping in some of the informed defaults, having more informed ranges for different types of components that you might see on the network. So I think we can definitely have some value add here, but the dream end state will probably require collaboration with industry to really build something like this out, where we have really informed parameters for all the different components that we might see on an electric power network. So that's the real challenge here, is just having the data. But this same process, I mentioned earlier that these different components of Simba can have value on their own. And I think this stage in particular can be really, really valuable, even if it's not connected to any other part of what we're working on. Whether you make high fidelity simulation models or not, one of the big challenges is just the time to put these simulation models together. And being able to automatically pull this information out would be extremely useful, I think, for speeding up this process. So again, the challenge is just creating the data set, but this could be a really useful component for simulation model development, whether that's within the larger architecture of Simba or whether it's not. But either way, so what comes out of this stage is a simulation model, but it's probably not super accurate. So it might be able to do some lower fidelity simulations, especially if we have the correct parameters loaded up in our reference library. So it might already be useful for some purposes. Maybe it can run, say, steady state simulation after going through this process. But if we had to rely on a lot of default parameter values, or if we want to do higher fidelity simulations, this model probably is not good enough just after this stage. No matter what, we would not consider this high fidelity because it's not fit to the particular network that it's describing. And so that's really what the next step of Simba does, is trying to do this fit to make the simulation model really, really precise to the real network. So this is where we're going to pull in a lot of machine learning to learn the correct simulation model parameters from operational data. And when I'm talking about operational data for these electric power networks specifically, I'm really referring to the frequency over time of electric generators. So this time series data is really our training data for the machine learning. So if we have this data from real operations, then we can use machine learning to identify those remaining unknown parameters, which would enable high fidelity simulation modeling. So again, we have a rough simulation model that comes out that can perform lower fidelity simulations, but to really do high fidelity simulation modeling with confidence, we have to have pretty accurate estimates of some other parameters that I don't think we'll know without really fitting it to the data of the specific network. So all that machine learning happens in this parameter identification process. That's sort of the bottom blue box here in this diagram. So a big focus of our research for this next year, and probably even moving forward farther than that, is just making sure that this process can scale to larger and larger networks. Because we're pretty excited by early results on small little test cases. We know there's a lot of potential for an application like this, but here the primary challenge is technical. So just making sure this process can scale, that's the biggest challenge with the model refinement stage. This is actually an engineering problem. Even though we know it'll be useful, we can get the data that we need. We definitely have some challenges to solve here before this can work on very, very large networks. Because just for a little context, if you look at the research literature on this problem specifically, the largest network that this particular process has been performed on and published on is a very well-studied 9-bus system. And even that's pretty recent. So, 9 buses, and bus is just where power is going into or out of the system, that's a really small network. So to really have this, work at scale, we're talking about hundreds of buses, maybe even thousands of buses for pretty large scale networks. So right now we're using these really well-studied systems just because it gives us smaller test cases that we can test out some very computationally intensive processes. As you can guess, this is a pretty computationally intensive process, which also becomes, increasingly more intensive, computationally intensive as we scale. But we can test out some of our computationally intensive processes, and using smaller test cases, we also can validate these models very well because we know how the network should behave because these are already very well documented networks. But eventually, we want to get this to a point where we can apply this to anybody's real world network, or the utilities real world network. We would validate against their historical operational data, and we would see that our model is working for their network. But real world networks are in the order of hundreds, maybe even thousands of buses. So we wanted to scale this up a lot more, but this is definitely an earlier stage research problem in terms of Simba. So again, want to highlight the model generation stage does not have technical challenges, it has a data problem. In this stage, we don't have a data problem, but we have a technical challenge. Either way, these processes can be very useful independently, I think. But either way, if we can get to a high fidelity simulation model through a process like SIMBA, what do we do with it? Why do these models matter so much? So I sort of alluded to this at the start, but you have a little more context for what we're trying to build. And I want to talk a little more about why it's so important that we have models like this. Because again, it all comes down to improving the efficiency of a network, which we really talk about just normal operations. How can we make sure the network operates as efficiently as possible when nothing is going wrong? And this is a lot of interest probably to utilities who, this is a cost thing for them. Then we're also interested in the reliability of the network. And we use the term reliability to talk about small and temporary perturbations. So a storm taking down a power line, that's going to be a reliability problem. How can a utility make sure that their network is reliable, can withstand some small issues that are just going to happen? And then we're also really interested in the resilience. And I think this is where a lot of focus is moving towards, where resilience isn't just about the small little challenges. It's about making sure the network still operates either as intended or as close to intended as possible under a big and rare catastrophic problem. If it does have to fail, we want to make sure it fails gracefully without causing even more problems, causing cascading failures, causing more harm, or loss of even human life. So it's all coming down to efficiency, reliability, and resilience. And our high fidelity simulation models can improve our ability to understand network behavior in all sorts of different scenarios for all of those different purposes. So there's a lot of different applications you can build on top of these simulation models. And different stakeholders are going to care about different things. So I mentioned earlier, I think that our team is really interested in this vulnerability analysis portion. That's really the interest of the Department of Homeland Security, particularly the Cybersecurity and Infrastructure Security Agency, who we work really closely with on this. But other stakeholders are going to care about different things. They might care about weather modeling. They might care about maintaining their network so it doesn't cause any issues. Whatever it is for these different stakeholders. So utilities are going to care about something else. DHS will care about something else. Different teams within utilities, I should mention, will also care about different things. Some are responsible for the reliability. Others are responsible for, maintaining the least cost, all of that different stuff. So all sorts of things can be built on top of simulation models. And right now, at least, we're not trying to build all of those different services. What we want to create is a really foundational service that enables all of those other people. Because what we want to do is we want to open the door to lots of different innovators so that they can go and make those applications that are going to improve the efficiency, the reliability, and resilience of electric power networks. Because we don't want to be the ones that are sort of the roadblock for innovation in this space. We just want to make sure that we can tap into the skills of anybody else that can make use of this. But to do that, we do have to be really careful about our design goals. So let me talk about the 4 design goals that are really shaping our past and future works. So the first thing on the front of our minds is that the whole value proposition of SIMBA is that it should make it easier to develop high fidelity simulation models. So we have to get this part right because this is the value add. We're not making better models than exist already. We already know how to make high fidelity simulation models. We already know how to make digital twins. The value out of SIMBA, what SIMBA is uniquely adding, is making that process faster, cheaper, easier. Now, the second design principle is that we are looking for a physics-based model. And this is really, really important for how we're using machine learning here. Because we don't just want a simulation model that can replicate normal system behavior. And this is the concern that would happen if you use machine learning to learn from operational data. Well, maybe you understand very, very precisely how a network will behave under normal system behavior. But if you don't have a certain perturbation captured within the data that you used in training, then how do you know that this model will generalize? And the way we get around this is by focusing on physics-based modeling. Because if we can use machine learning just to identify the real underlying physics equations or the parameters that inform those equations, then we can have much more accurate equations, more accurate models. And that gives us confidence in our simulations of rare events, even events that have never even happened before, because we understand the physics, not just replicating what we've seen before. Now, the third thing is, and this really gets to the idea of opening up innovation, is that we want to keep this open source as much as possible, at least right now. So one part of this is we don't want to put people into proprietary technology. We want to avoid that vendor lock-in because we want to be able to collaborate with people on this. We want to be able to share this with other people, and we don't want them to have a particular stack of tools. And the other part of this is we just want to make it easy to customize and build on top of Simba. And that's a lot easier when you have open source tech. And then lastly, the other thing here is that we've been really focusing on the electric power sector so far. We looked a little bit into natural gas as well, but electric power is really where we've been focusing. But we don't want to design an architecture that only works for electric power. We really want the architecture of Simba to apply to all critical infrastructures, because then even though some things might change, certainly the type of data that you expect might change, the timescales might change, we still want the general architecture of Simba to work for all of these different infrastructures so that we can extend the same idea to other infrastructures and help rapidly build simulation models for them as well. So again, we really want to see Simba become a really powerful resource, not just for simulation model building for electric power sector, but really for any sector. We think these simulation models be really powerful tools for protecting, improving the nation's critical infrastructure. And because of that, we want to make it as easy as possible to get these high fidelity simulation models into the hands of all the right people. So a lot of the work we've done today could be applied to other critical infrastructures, and it'll take more work to scale them up to those different infrastructures, but we definitely want to lay the groundwork for continued work. So that's my last slide. I'm happy to answer any questions for the remaining time. I can't talk about everything. There's some parts of this work that haven't been publicly released, but I think I can talk a lot about it. And there are also some things I might have to connect you with some of my great engineers about. But hope I can answer some questions if anybody has any.
Yeah, Charles, thanks for a great presentation. So now it's time for questions. So either you can raise your hand or post your question directly into the chat window.
Hey Charles, this is Hussein Ushar from New York Power Authority. Thank you for your presentation. I was just wondering if the power grid is the only system that you guys have worked on. Have you applied the same methodology on other systems prior to starting with the electric power systems?
Yeah, so in terms of the model assembler process, specifically this model generation stage, we also looked briefly at natural gas. We are kind of interested in applying it there. And I think a lot of the same principles apply. So we did some preliminary work on that. In terms of the model refinement, though, we've only looked at power because that's a little more, I think, unique to particular infrastructures. The model assembler process, I think, can work with basically any graph. It's a lot more flexible there, whereas the model refinement and training a machine learning model that can learn from operational data and understand the precise parameters, that's a little more specific. So that one we've only focused on power. I think same principles can be applied to others, but we haven't done anything with it yet.
Okay, thank you.
Hey, Charles, this is John Dirkman with Resource Innovations. That's an excellent presentation and a very necessary work that you're doing. My question for you is how or when can we have access to Simba?
Yeah, great question. So some of it's out of my control. I'm definitely pushing for, this just got publicly released recently, so now we can at least talk about it. In terms of sharing, I think what we're looking for now, we are looking actively for beta testers. And I should have mentioned this, and I'll put this out to this audience, is that we definitely want to start testing this out on smaller, real world networks and test cases. And if people want to collaborate with us on that, we're super open to that because there's only so much we can learn from our pretty small test cases and whatnot. So I think for early testing, that's sort of open now. If people have data to bring to the table, we'd love to collaborate on that. And then in terms of this, really being ready for to be published to the world. I'm not sure. I think it'll depend on what we find from those first experiments. Again, as I mentioned, there's kind of very different types of challenges to solve between these different components of Simba. So yeah, I guess I'll leave it there, and I'll put my email in the chat too, so I can be contacted. I'm not sure if people interesting. I haven't seen Simba.ai. I see somebody put that in chat, and I have I'm not responsible for that website, so I'll have to check that out. That might be a completely unrelated thing. But I just put my email in the chat. If anybody would thinks they'd sort of be a good beta tester or has any questions, contact me for any reason. I think there's also, a little bit of sensitivity around, having high fidelity simulation models is great for the right people. It's also maybe dangerous for the wrong people. So I think there's still some questions around how this will be shared and published and what that will even look like. But those aren't really answered yet at this stage of research.
Good answers. And definitely sign me up and I'll email you as well. Thank you.
Awesome. Thank you very much.
Any other question? Hearing none. So yeah, thank you, Charles. Thanks for a great presentation again. And with that, I think we have Hussein. He will provide some update on the task force, particularly on the